Hello, I'm Jim Dabney of the University of Houston Clear Lake, and today I'll be talking about using assumed guarantee contracts for development verification of autonomous spacecraft. My co-authors in this work are Pavan Rajagopal of CACI and Julia Badger of NASA Johnson Space Center. So today I'll be talking a little bit of background about why we're using the assumed guarantee contracts for development verification. Then I'll talk about how we define and format the contracts, state machine design patterns, and implementing the state machines and assumed guarantee contracts in PlusCal and the TLA Plus system. And then we'll show using the TLC model checker that's part of the overall package that includes PlusCal and TLA Plus for checking assumed guarantee contracts, and then lessons learned and what we're going to do next. As we all know, the spacecraft systems are becoming more complex and more autonomous. We're working on the Gateway Vehicle Systems Manager, which will manage the spacecraft for extended unattended operations and monitor and control the numerous subsystems and modules. The Vehicle System Manager also transitions between various levels of autonomy depending on the presence of crew and ground-based contact. The traditional approach to verification that's been used on aerospace systems can be represented using the verification V. We start on the left side with the highest level of needs assessments, then requirements development, architecture definition, detailed design, and implementation. Once the implementation is done at the lowest level of the compilation unit, then we do unit testing, and then additional testing at each level as the integration proceeds. So this approach has been proven effective over the years, but it has some serious drawbacks. The biggest problem with it is that about 70% of the faults are introduced early in the life cycle, mostly in requirements development, but they're not found until very late in the life cycle. So we've learned that if we find those faults that are introduced in the requirements phase in the system integrated testing phase, then it's going to cost as much as 100 times as much to fix a fault. So the approach that we're using is attempts to put as much verification early in the life cycle in the requirements development phase so that we can find those problems early and fix them at a much lower cost. The approach that we're using is based on assumed guarantee contracts. Assumed guarantee contracts define the expected behavior of the systems, subsystems, and components. The assumptions or preconditions on the system's inputs bound the conditions in which the contract applies, and the guarantees or postconditions declare the conditions that the output must satisfy and can serve as verification goals. So we can use contracts to define safety properties or hazard controls. And an example would be a car shouldn't start unless the transmission is in park. So then we can convert those assumed guarantee contracts into a mathematical specification, which we can model check using one of several standard model checking tools to ensure that this specified system has the desired behavior and safety properties. We define each assumed guarantee contracts using a standard template that consists of 5 parts. The variables are inputs and outputs. The inputs are the values or the things that are supplied to the function, and the outputs are the values or things that are returned from the function. The data types of the input and outputs could be anything. For example, they can be scalars, database records, arrays, or structures. The assumptions are the conditions and the constraints on the inputs under which the contract is valid, and guarantees are conditions on the outputs when the contract is valid. If the assumptions aren't satisfied at any moment, then that particular contract is not active. We can verify the assumed guarantee contracts for development verification using either traditional scenario-based testing or contract specification and model checking using model checking tools. The benefit of model checking is that it's exhaustive. That is, it explores every path through the mathematical representation of the system automatically. We don't have to generate test vectors to stimulate the system to go through each path. The model checker does that automatically. The drawback is that developing models of suitable fidelity is expensive and can be labor intensive. So we recommend that we select the assumed guarantee contracts that we model check based on complexity of system behavior and the potential for contract violation to have adverse effects on the mission. And by complexity here, we mean the functional complexity of the system. So indicators would be the number of execution paths, that's states and transitions, and the number of interacting and interdependent applications. A single application with a limited number of paths is fine for traditional testing approaches because we can see all of the paths and easily verify that they're covered. When we have multiple states and paths or multiple interacting applications, for example, when we have state machines that involve a lot of concurrency, then we have potential for deadlocks, race conditions, and other emergent behaviors. And in those cases, traditional testing may not be adequate. And as the state machines themselves get to be more complex, the viability of traditional testing decreases considerably. So those are the situations that are good candidates for formal specification and model checking. And along with criticality, we're also interested in the potential for mission impact. So those contracts that merit model checking should reflect critical properties of the system and things that, if the contract is violated, can result in hazards, mission impacts, or off-nominal behaviors. The system model consists of state machines and assumed guarantee contracts. A state machine represents the configurations of the systems, and it represents the feasible transitions among the states. Assumed guarantee contracts can be represented using propositional logic and linear temporal logic, depending on the contract. And we're implementing them as assertions and linear temporal logic formulas that are evaluated by a model checker. We can organize the parts of the state machine as a set of separate lists of states, Q, events, sigma, and transitions, where each transition is a triple that consists of a state, an event, and a next state. A data structure representing that system consists of a list of states, and for each state, there's a set of event transition pairs. So an event node could be, for example, a list that consists of an event and a corresponding next state. And again, these are associated with the initial states. Next, I'll talk about state machine design patterns using this simple example state machine. So in the diagram, the boxes represent the states or the configurations that the system can take on. The arrows represent the transitions, and the numbers and the letters on the arrows represent the events that correspond to the transitions. So here, if I'm in state 1, event D occurs, I stay in state 1. If event A occurs, I transition to state 2. And if event B occurs, I transition to state 3. If I'm in state 2, only one event is possible, that's state A. So if I'm in state 2, the state A is the only thing that can happen, and I stay in state 2 forever. And then the third state, state 3, has no transitions from it, so it is a terminating state. Our first design pattern is state-based, and in this approach, that using a switch case or the if-else structure, we organize the state machine about the states, and then for each state, we check for each of the feasible events that corresponds to that state, and then set the next state used based on the possible event. We could also organize the state machine using a design pattern based on the events, and then instead of stepping through the the possible states, we step through the possible events, and then for each event, we check for each feasible state. So it's the same sort of structure, but instead of organizing about states, it's organizing about events. Our next design pattern uses the goto construct, in which the next state is computed as a function of the event. The goto pattern is limited in scope, so it doesn't have the drawbacks that gotos typically have in programming languages. The design pattern that we're using is the state approach that we looked at on a previous slide. So here I've implemented that simple state machine model in the PlusCal language, which is an algorithmic extension to the TLA Plus model checking system. The core of the model is the while loop that steps through the set of possible states. And so if we look in detail, you can see that if the first state is 1, then either the next state is 2, or the next state is 3, or the next state is 1. So what this means that it's going to either take a transition to state 2, a transition to state 3, or stay where it is. And then if the next state is 2, then the next state after 2 is also 2. That's because it loops back to 2. The only place it can go is where it is. So it's stuck there. And then if the state is 3, then the next thing it does is done. So note in the model itself, I don't have explicitly stated the events. The reason that I don't have the events is I don't need them to do the model checking. I've defined the state machine itself and the transitions in the model checker. When I check it using the TLC model checker, is going to take each of the possible transitions. And so it's going to generate a set of timelines for each of the things that can happen. So for example, one timeline will be state 1, then state 1 again, then state 1 again, and then state 3. Another timeline would be state 1, then state 2, then state 2, then state 2, where it's stuck in state 2. And so the model checker checks each possible transitions. Therefore, it's not necessary for me to generate the list of events to stimulate the system to take each of those transitions. We check the model by first compiling that PlusCal model to TLA Plus, which is done automatically using the graphic tool. And then we check that TLA Plus model that's generated from the PlusCal model using model checker TLC. The model checker tries each possible timeline through the system, and as I said, either produces multiple parallel timelines. And so instead of stepping through the system one time, it's going to step through it many times. If I have parallel or concurrent processes, I can have millions of different timelines that it's going to check, and it does it fairly quickly. Also note that state 2 leads to itself only, so the model checker should find a live lock there, because that is that the system won't terminate. So again, our contracts can either use invariants or temporal formulas. Here is an example of an invariant. Given the variable spares available that tracks spare parts, there's always going to be at least one spare available. So we then would define the invariant in PlusCal using the define statement. Here, spares always is defined to be spares available is greater than 0. And again, this is an invariant, so that when I use the model checker, it has to be true all the time. I can also define contracts using temporal formulas, and a similar kind of a temporal formula would be given the variable spares available that tracks spare parts, eventually there will be at least one spare part available. So we could write that as a temporal formula, also using the defined structure in PlusCal, where I say spares available is defined to be eventually, that's what the diamond indicates, the variable spares available will be greater than 0. I can check the contracts then using the TLC model checker. And so this is the interface for the model checker, in which I can identify or declare temporal formulas and invariance. So there's a box here for invariance, and so you can see in the bottom I have the spares always invariant listed and in that checked. So now when I run the model by pressing the little green start button, the model checker will check for that invariant and to see if the spares always is true. It's also possible in TLA Plus to check the temporal formulas, and there's another box that has a temporal formulas in it. And so in that box, it has termination, which is a built-in temporal formula, and that essentially checks for live locks. And then the spares eventually the other temporal formula that we wrote. So again, when I run the model using the little green start button, what it does is it checks every timeline through the model, and it checks every invariant that's active and every temporal formula that's active. And when it finds one that fails, then it stops and reports the failure as an error. We're finding that there are plenty of opportunities for us to use the assumed guarantee contracts and model checking in the Gateway Vehicle System Manager. And we're also finding that using the templates for the state machines accelerates their development and provides a standard format that everyone can understand. We're continuing to develop more complex concurrent state machines that include multiple instances of processes and resource sharing, and we're also increasing the scope of the contracts. That concludes my presentation. Thanks for listening, and I hope that you found this to be useful.